We can also find the moment of inertia of the circular region about the center. If we have an ij increment with sample point x star, y star, how far is that increment from the center, from the axis of rotation? Now, the axis of rotation is an axis perpendicular to the lamina through its center. Okay, well, the Rij is just the hypotenuse of this triangle. The legs of the triangle, of course this point here is 1, 2. The legs of the triangle are xi star minus 1 and yj star minus 2. So this Rij star, distance from the axis of rotation to the sample point in this increment, is just the square root of the sum of the squares of these two things, which actually coincides with the density function. Now, there's no reason they should even be related, but just coincidentally that's what we get. So your moment of inertia, your contribution to the moment of inertia, of course, is the product of the mass times the square of its distance from the axis of rotation. So the delta Ij is the delta Mij times the Rij star squared. And you could put a star in the Mij and a star in the delta I if you want. Your I, then, is the double sum of the Mij times Rij squared. Put a star in the Mij. Not really necessary, but we do it. Which means that you're going to have this integral, where the delta Mij has an x minus 1 squared plus y minus 2 squared for the density times the area, and then multiplied by Rij squared, and Rij squared is just the xi minus 2 squared times yj minus 2 quantity squared, matching this, giving us the square of that expression. So this would be the expression for the moment of inertia. And that's related to the energy you attain if you get this thing moving, rotating at a certain rate. Given the rate, you use a moment of inertia. Take 1/2 moment of inertia times the angular velocity squared, and you have the kinetic energy, but that's physics. So, okay. Now, as another example, you got a triangle, 3 points. 3 points given, the origin 1, 1, 0, 7, and we're asked to find the center of mass of this region. And we could also find moment of inertia, we could find mass given a density function. Well, density function here is just going to be x plus y, meaning the further you go this way, the more density you got, the further you go this way, the more density you got. So the thing gets denser as we go from here up to here, and as we go from left to right. We could describe the region very simply. Now, to describe the region, I say, okay, well, if we do a line through here, the line is x equals y. Goes through the origin, goes through 1, 1, the line is x equals y. A line through 0, 7, and 1, 1 is y equals 7 minus 6x. Easily obtained because you know the y-intercept is 7, and you calculate the slope, goes down 6 over 1, slope is negative 6. There's your function. If it's more complicated, you can use a point-slope form, point-point form, whatever, to find the equation of the straight line. Now your typical increment here, now you're partitioning x from here to here, and then for every x, you're partitioning y from here to here. Your typical increment that you get is a distance yj star from the x-axis and at distance xj star from the y-axis. I didn't write the distance from the y-axis down. This with your description of the region, x goes from 0 to 1, and for any x, y goes from x, y equals x, up to 7 minus 6x, y equals 7 minus 6x, giving us these limits on the integration. We integrate the density times the area, and there's our mass. If we want the x moment, then since our typical increment is a distance yj star from the x-axis, we're going to have to multiply the mass of that increment by its distance from the x-axis, yj star, which will give us a y here. And for my, we're going to have to multiply by x for reasons that are totally analogous. Now if we want the center of mass, we divide the x moment by the mass, the moment about the x-axis by the mass to get the y-coordinate, and divide the y moment, the moment about the y-axis by the mass to get the x-coordinate for the center of mass. So we're going to use these in the prescribed manner. That's not too difficult to understand. We could also do a moment of inertia about the point, say, 1, 1. We can do it about any point. Moment of inertia about the point 1, 1 is this integral, where we have the square of the distance from 1, 1 to xy here, so that's like your r squared, and your density here, and your area here. So density times area gives you mass, and this is the square of the distance from your point 1, 1. Integrate that, you have your moment of inertia.